Hello fellow computer enthusiasts, my name is Christian, hope you're doing well today. In today's video we will talk about the DeskPi Super6C, which is a Raspberry Pi 4 compute module cluster board that comes in a pretty handy mini ITX form factor and that supports mounting up to 6 Raspberry Pi compute modules. We will use it to further improve my existing home network by adding additional features and reliability while replacing 2 of my already existing and really hardworking Raspberry Pis. And yes, you might already know one of these Pis from my previous videos where I introduced the Docker container setup that I use as of today to provide services within my home network that do not run on my beefy Threadripper based Unraid servers. Currently, I try to port as much services as possible to a low power consumption server like the Raspberry Pi or the new DeskPi cluster, in order to ensure 24/7 availability without paying thousands of dollars each year for my energy bill. And the best thing we will also clarify today, if you need a Kubernetes cluster in your home network, and if so, how to install Kubernetes to multiple Raspberry Pis, build a cluster, and how to migrate existing services from a Docker-based setup into the new Kubernetes cluster. But before we deep dive into today's topic, let's have a quick look on the content so that you know what to expect from this educational video. Let's start with a quick unboxing of the DeskPi Super6C that shipped with a small manual, the ITX board itself, as well as a power brick. But in this video I will utilize an existing SFP Plus power supply that I already own and that is also supported by the DeskPi Super6C. You also get the screws for the NVMe SSD and that's it. Unfortunately, for the price of $199, you won't get any Raspberry Pi compute module that is needed to operate the board. So to start the project, I bought 3 of them separately, and due to its low availability in the current market situation, they were pretty expensive, and they all come also in different RAM and flash configurations. It doesn't matter much for my use case with Kubernetes, because I plan to utilize NFS shared SSDs connected to the first compute module, but it's annoying because it makes setting up the operation system for the different Pis a little bit more complicated. The DeskPi Super6C mini ITX board comes with a lot of I/O ports, but most of them seem to be wired to the first Raspberry Pi compute module. Both HDMI ports as well as the USB 2.0 ports are dedicated to the first compute module. Every compute module has also access to a dedicated micro USB port that is needed in order to flash the boards if you put a compute module with onboard eMMC storage into a slot. The only shared ports are the Ethernet ports, which are directly wired to the internal 1 gigabit switch, as well as the DC-in power connector and the compute module activity LED matrix, which is a pretty helpful feature in order to identify bootloader issues, I can tell you. Each compute module is also connected to an SD card slot and a dedicated NVMe PCI Express port, which are both located on the bottom side of the DeskPi Super6C mini ITX board. Before we now talk about Docker, Kubernetes and the software side of things, let's build a cluster with spare parts that I already own from my previous projects. So what is Kubernetes? That's a pretty good question, and according to their own website Kubernetes.io, it is the following. Kubernetes, also known as K3s, is an open source system for automated deployment, scaling and management of containerized applications. It groups containers that makes up an application into logical units for easy management and discovery. I guess that might not answer all of your questions regarding the technology, and especially not why you should consider Kubernetes for your home lab. To understand what Kubernetes does and what it's good for, we need to understand first how virtualization and containerization works in general. What are they good for and what kind of problem they solve when deploying applications. So back in the days, there were only physical machines running an operation system directly on top of a hardware layer, and applications were directly installed on top of the operation system. That introduced some interesting problems when it comes to deploying applications, which are usually solved with virtualization or by buying more physical servers, of course. Imagine we want to run two different applications and both need a system library as a dependency, but in different versions that is complicated to realize on the same operation system. Or even worse, imagine we have a software that is only able to run on a Windows server and another software that is only available for Linux, and we need to run it for the same customer. In this case, we would have to buy two different physical servers in order to make both software run. The next issue is related to cost, because BareMetal servers were used to be used by just one tenant, meaning that the server was often idling most of the time, because the full hardware performance were often just utilized by just one application. Most of these issues, and a lot more that we haven't discussed so far, were solved by introducing a new layer between the hardware and the operation system, called a hypervisor, that makes it possible to share the physical resource of a machine across different so-called virtual machines that do all run their own operation system. That makes it possible to operate, for example, Windows and Linux on the same physical machine, and it also allows to share a physical machine between different tenants in order to minimize idle time and maximize resource utilization. Looking again on our use case of hosting different applications, we see another problem in front of us. Imagine we isolate our applications into separated virtual machines. That's great. Now they can all use the same shared hardware and get their binaries and libraries, so all the dependencies in the version they need. Really good. But to be honest, now we have to spare a lot of resources to run multiple versions, often of the same operation system, which also takes up a lot of storage space on our physical machine. And that's where containerization comes into play. Containers and virtual machines are very similar resource virtualization technologies. Both allow to share hardware resources such as RAM, CPU, GPU, and storage, as well as networking. The key differentiator between containers and virtual machines is that a virtual machine virtualizes an entire machine down to the hardware layer, and containers only virtualize software layers above the operating system level. Containers are lightweight software packages that contain all the dependencies such as system libraries, third-party code packages, and operation system level applications required to execute the contained application. Every container that you will see in my videos are utilizing a technology called Docker, but that's not the only container technology out there. You can achieve the same thing with tools like LXC, which stands for Linux containers, or Rocket. But what does Kubernetes stand for? Because it's not another container technology, right? While Docker provides an efficient way to package and distribute containerized applications, running and managing containers at scale is a challenge with Docker alone. Imagine you would have to coordinate and schedule containers across multiple servers and clusters, and you need to upgrade and deploy applications with zero downtime. And monitoring the health of containers in real time can also be very tricky with just Docker alone, right? To solve these problems, solutions to orchestrate containers emerge in the market. Tools like Kubernetes, Docker Swarm, Mesos, and others that allow to manage a large volume of containers and users, balance load efficiently, offer authentication and security, as well as multi-platform deployments and more. So in our homelab example, Kubernetes helps us to distribute our container within the Raspberry Pi cluster and takes care of all the heavy lifting that would otherwise be very hard to do by hand. Okay, in our home setup that might be not necessary. And in general, Kubernetes is simple. You just describe in something called a manifest what your desired application state will look like, and Kubernetes takes care of the rest. For example, we could just define that we want to have at least two containers running Pi-hole and that we want to access the application by our DNS name pi-hole.iltpwc.com. Kubernetes then takes care of deploying the container, or in this case a pod with the containers running Pi-hole, for us and distribute it across the available resources within our Raspberry Pi cluster. But we will come to that in detail later. Now that you have a basic understanding of virtual machines, containers, and the need for orchestration tools like Kubernetes, we need to clarify a few terms before we have a look on my current Docker-based setup and before we migrate the existing containers into our new Raspberry Pi-based Kubernetes cluster. Pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. In general, a pod is a group of one or more containers with shared storage and network resources and a specification to run the container. A pod is similar to a set of containers with shared namespace and shared file system volumes, executed in a non-cloud context in the same physical or virtual machine, or on the same logical host in a cloud context. Pods are non-permanent resources in Kubernetes, and they get created and destroyed to match the desired state of your cluster. A Kubernetes service is a way to expose an application running on a set of pods as a network service. Kubernetes gives each pod their own IP address and a single DNS name for a set of pods so that we can load balance across them. Services provide a way to communicate with these pods without the need of manually tracking the IP addresses and rerouting traffic between the pods. The service is responsible for exposing an interface to the pod which enables network access from either within the cluster or between external resources or processes. There are different types of services available in Kubernetes, which I would like to explain before we go into my migration experience. The default type is something called a ClusterIP, which is used to expose an IP address internal to the cluster. In this case, access is only permitted from within our Kubernetes cluster. The ClusterIP is also the baseline to implement all the more complex or high-level functionalities like Ingress or LoadBalancer, but we get to this later. The next service type is called NodePort. If you use a service from type NodePort, Kubernetes will open a certain port within a specific range, something between 30,000 and the maximum number, which is 32,776 on every node in your cluster. That is basically the foundation for other higher level methods of Ingress, such as load balancers, but can also be useful in development to access your application from outside the Kubernetes network. NodePort configuration will automatically create the cluster IP to route the traffic internally. I mentioned the term Ingress a lot of times, and what I mean with Ingress is some kind of an API object which exposes HTTP and HTTPS routes from outside the cluster to services within the cluster. The traffic routing is controlled by rules predefined on the Ingress resource. The Ingress can be configured to give services externally reachable URLs, load balance traffic, terminate SSL and TLS, and offer name-based virtual hosting. The Ingress is part of the Kubernetes cluster and runs as a pod. The Ingress can be an internal cloud one like AWS or GCE provided, or a general one like Nginx, and also third-party software like traefik that was used in my Docker to Kubernetes migration adventure. A load balancer exposes a service using the cloud provider's load balancer mechanism or using your own one like metallb, and automatically creates the necessary node ports and cluster IPs to route the desired traffic. In general, a load balancer efficiently distributes network traffic across a group of servers, or in our case, Kubernetes pods. They are needed to serve services that have thousands, if not millions, of concurrent requests from users, like the YouTube website that you are currently watching. The load balancer performs the following functions. It distributes client requests on network load efficiently and rule-based to our pods, ensures high availability and reliability by sending requests only to pods that are available and online. And for our Kubernetes use case, it also provides the flexibility to add and subtract resources, or in this case pods, as the demand dictates. In a future video, I will explain the different algorithms that can be used to load balance, like round robin, where you essentially distribute traffic in a sequential order, and all the others, so make sure to like and subscribe if you are interested in learning more about load balancers and computers. Okay guys, let's go into today's topic and let's try to migrate my existing Docker container setup into our new Kubernetes cluster. At first I will start with the installation of the DietPis, and after that we will install Kubernetes, and then we will try to port the load balancer as well as traefik in order to get our services running in the new K3s cluster. I like to go with the DietPi distribution on my compute modules because the distro is very lightweight and, according to their own website, 3 times smaller than the Raspbian Lite distribution. It also runs only necessary services, meaning that it has a very low memory footprint at runtime, so that we can utilize the full compute module resources within our Kubernetes cluster. It is also the distribution that I'm very familiar with because I have used it on my existing Raspberry Pi setup with the Docker containers. And DietPi is also pretty handy when it comes to headless configurations and installation, because they offer an automatic first boot installation, which you can fully configure by a text file that you can find in the boot directory called dietpi.txt. To install DietPi on the compute modules, we have to download DietPi and have to flash the SD cards for the compute modules without eMMC storage, or we have to flash the eMMC storage that are already on the devices. So the first thing that we need to do is to install Kubernetes. In our case, we will choose K3s as our cluster, and it's pretty easy to install because you can download the installation script. The only thing that is necessary is to disable the inbuilt load balancer by adding the disable service LB, as well as disabling the inbuilt traefik that comes with K3s. So in our case, we have to provide some environment variables, disable service LB, as well as disable traefik. And then we are good to go. The next step is to get our token so that we can install the clients and also let the clients join our master, which you see on the right hand side of the display, where we execute the script, also with the IP address of the master node, so that they can work together in a cluster. The next thing that I do here is to add them in my Wether installation. Wether is a very great tool to get a visual overview, so a web interface to see and access your Kubernetes cluster. And in order to do so, you have to add a new cluster in Wether, and then you get an easy command that you can execute in the master that will install the control component of Wether so that the agent can join, and then you can see all your Kubernetes ports and resources in a fancy web interface. Next thing that we will do is to install the metallb load balancer, and you will find the full source code on GitHub. I will share this below this video. And after that, we will install our traefik, and you will also find the configuration in the GitHub repository as well. So let's summarize everything that we have discussed so far. The first thing that I would like to say is that the cluster board Super6C is really awesome, and I plan to add new compute modules over time, and I have already ordered the next one to add these to my Raspberry Pi cluster. Then we also learned a lot about virtual machines, containers, and also about container orchestration with Kubernetes, but I guess it is necessary to have another video to go more into details. And we also haven't migrated many services that are currently existing in my Docker area, so we also have to do this in future. But for now, I will stop this video here. So thanks a lot for watching this episode of ILTPWC. Stay tuned for the next one, and I promise that will be better than this one, because to be honest, I'm not very satisfied with the result. It took me a lot of time to create this video, but I currently have the feeling that I could have done this much better. For me, it's the first time to start out with YouTube, and therefore I'm new to video creating, and I still have to learn a lot of stuff, especially how to write scripts that are effective and that are easy to create and to make, because my main goal is to teach how all that stuff works. And for this video, I do not have the feeling that it provides much value, but I already invested a lot of time, I guess currently 6 weeks, and therefore I decided to upload this video. Okay, if you want to follow me on my YouTube adventure and also to learn something about computers, please subscribe and like this video. It does a lot for me. So thanks a lot for watching, and I see you in the next video.